This is topic 2, Principles of Motion of Water. The contents are as follows. 2.1, what is water as liquid and as fluid? 2.2, Newton's law of motion for water. 2.3, conservation laws. 2.4, methods of description of motion of water. 2.5, equations of motion of two-dimensional flow in Eulerian coordinates. 2.6, equations of motion of three-dimensional flow, Navier-Stokes equations. 2.7, equations of motion of three-dimensional flow, Euler's equations. 2.8, equations of hydrostatics. 2.9, integration of equations of motion, which is Bernoulli's equation. Hydraulics involves water either in motion or at rest. Let us make sure what are the important differences among solid, liquid, and gas. Water is liquid, and liquid is a fluid and is a continuum. So most of the principles of fluids and continuum apply to water. The important points are: solids have fixed shape and volume by itself, such as aluminum cylinder shown here. Liquid, including water, has fixed volume but not fixed shape, so it adjusts to the shape of the container, which keeps the liquid from moving. Gas, on the other hand, does not have fixed volume or fixed shape, so it takes the shape of whatever container and usually fills the entire space. Solid, liquid, or gas is kept at rest or resists motion by resisting forces. Solid generates resistant force when it is deformed. Fluid, liquid, or gas generates resistant force when it moves. So in order to keep fluid at rest, the container must be shaped to counterbalance the gravitational force by pressure. A channel cannot contain gravitational force, so liquid keeps moving until the shearing resistance due to the motion balance the gravity. Gas generates pressure by changing its volume, so it can be contained by expanding to the volume of the container. The motion will be all governed by Newton's law of motion. For those who are not quite familiar with the Newton's law, these are the three laws: first law, second law, and the third law. So we review Newton's law of motion for water. For solid particles, Newton's second law can be applied to the solid body directly, since it stays as one body with fixed mass. It accelerates as the force is applied to it. Then for liquid and gas, the shape is not fixed, so we must apply the law to fixed parts of the whole part of the liquid or gas as it moves and deforms. So for the motion of water or liquid, the Newton's laws are applied in the context of conservation of momentum and used with conservation of mass and conservation of energy in fixed parts, for fixed parts. Since the water is incompressible in most situations, the kinetic energy and the internal energy are independent, except viscosity converts kinetic energy to thermal energy by small amount. So the conservation of law of mechanical energy, which is kinetic and potential energy, is equivalent to the conservation of momentum. Basically, there are two methods of describing motion of fluids. The first method is the Eulerian method, in which flow quantities are described as functions of fixed position, say x and y coordinates, and at time t. This is what is usually used in hydraulics when the flow is looked at from a fixed observer, like a person standing on the side of a river. The second method is Lagrangian method. With this method, the flow quantities such as velocity and pressure of a fixed fluid particle or element following its motion are described as functions of particle with given initial or reference position. These positions are often designated by Greek symbol psi and eta to discriminate from Eulerian coordinates x and y. The equations of motion for two-dimensional flows in Eulerian coordinates are as follows: the conservation of mass and conservation of momentum. First, the conservation of mass requires that the amount of flow going in and the amount of flow going out of a control volume, say like A, B, C, D, a balance. If U and V are the velocity components in x and y directions, the results is like in equation 2D-1. The conservation of momentum for the fixed volume, the same fixed volume A, B, C, D, is as follows. Say the conservation of momentum in x direction requires that the sum of forces acting in the x direction equals the change of the momentum, which is the mass times acceleration in x direction of the same volume. If we consider the pressure and viscous stresses change in space, the sum of these forces acting on the four surfaces of this volume is like equation parenthesis A. The acceleration in x direction of the same volume is given by equation B. If they are equated, we obtain equation 2D-2, which is the equation of conservation of momentum in x direction. And similar equation for y direction becomes like 2D-3. These are the basic equations of motion in 2 dimensions. Similar derivation for 3-dimensional flow can be made with velocity components x, y, u, v, w in x, y, z directions. If y is taken vertically upwards, the gravitational force rho, the density of water, times g, the gravitational acceleration, is added in the negative y direction in the equations of motion, in the equation of motion in y direction. The results are equations 3D-1 to 3D-4. These are called Navier-Stokes equations. The special case of zero viscosity or small viscosity, all terms with tau in the equations of motion are zero. Such flow is called inviscid flow or ideal flow, and the equations reduce to what is called Euler's equations, 3D-5. These equations are used when viscous or turbulent effects are very small and used in various applications of hydraulics. Now, when the water is at rest, the acceleration is zero, so the forces acting on the fluid element balance. The forces are only the pressure and the gravitational forces, since the viscous forces are generated only when the fluid is in motion. The equation of motion simplified to the following. These equations are integrated to a single equation. Const, C-O-N-S-T, is related to the position where the pressure takes a prescribed value, such as the water surface, where it is equal to the atmospheric pressure. What should be noticed here is that this equation is meaningful only when there is a point or a surface where the pressure takes special value, like atmospheric pressure. Now, when the water is not completely at rest, but if the acceleration in the vertical direction y is zero or small, then the equations can be simplified. And if the viscous terms are also small, the second equation still holds. There are many cases, including some complex flows, the acceleration in the vertical direction is small. Then the hydrostatic pressure distribution given by this equation will still hold. In fact, we make the assumption in many flows when the acceleration may not be very small, but with some adjustments. The equations of motion can be integrated in space in special cases. The result will be very useful. Here we show how they are derived. If the flow does not change with time, i.e. steady flow, the time derivative in the acceleration is zero. Then the acceleration term in the left-hand side of the equation of motion in x direction can be rearranged as follows. The quantity in the parenthesis is called the volticity. The volticity can be zero or very small in many cases. Then it may be ignored and the acceleration term can be written as the x derivative of 1/2 of the square of the total velocity, like in the next equation. The term on the right-hand side is pressure and gravitational force, which can also be written as the x derivative, and the entire equation becomes as follows, as the next equation. The similar manipulation can be made with the equation for y direction, which will have the gravitational force if it is the vertical direction. Then they can be integrated in arbitrary x and y directions to give the following equation. Note that there is an integration constant. Now, the last equation obtained by integrating the equations of motion is called Bernoulli's equation. This Bernoulli equation can be written in a few different forms. Third equation writes the constant as variable h. That allows an approximate relation for flows that do not strictly satisfy the assumption of zero volticity or the irrotationality, which is satisfied in inviscid flow with negligible viscosity and negligible effect of turbulence. The three terms on the left-hand side of this equation are called the velocity head, pressure head, and elevation. The equation will be useful in many analyses used in hydraulics and should be fully understood. The meaning and the limitations should be fully understood. This is the end of the principles of motion of water.